Hello engineers, welcome to Engineer Brandon's Tools. So we move into analysis of control systems, our first lesson. So analysis of control systems is done with MATLAB. Three ways of defining transfer functions with MATLAB for the analysis of control systems. We'll be defining the transfer functions using examples. For instance, let us take a function h of x equals this. So let us define a transfer function in MATLAB. So there are three ways of doing this. So there is the TF method for defining. There is the S equals TF of S method, and there is the ZPK method. So let us start with the TF method. So with the TF method, to define this transfer function, here in my command window, I can simply type h equals TF bracket, then inside I put square bracket. So inside this square bracket, I have the coefficients of S and powers of S with the constant term of the numerator. So I notice that here is my numerator. There is only a constant term, no coefficient of S. So I'm going to enter 100 since 100 is the only constant term. So I'm going to enter 100. Then for the second square bracket, it deals with the coefficients of S and the constant terms for the denominator. So here is my denominator as s squared plus 6s plus 100. So I'll have coefficient of s squared, coefficient of s, and the constant term. So coefficient of s squared in this case is 1. So I'm going to enter 1. I'm going to leave a space. Coefficient of s is 6. I'm going to enter 6, leave a space. Then constant term is 100. So I'm going to enter 100. So my transfer function has been defined. So if I hit my enter button, I'm going to see h as this, exactly the same as here. So it defines it as a continuous time transfer function. So that is the first method of defining transfer functions with MATLAB. So for your assignment, I'm going to give you a transfer function that you can define. So define this transfer function I of s equals this. You can pause the video and try to work out. Let's define that transfer function. So I'm going to write I equals TF. So for the first square bracket, coefficients of s and powers of s with the constant terms. So I have as powers of s, s square and s. So coefficient of s square is 1. I'm going to enter 1. Coefficient of s is negative 6. I'm going to enter negative 6. Constant term, there is no constant term here. Constant term is 0. So I'm going to enter 0. Then for the second square bracket, coefficients of s and powers of s with the constant terms for the denominator. So I have coefficient of s cubed here is 1. So I'll enter 1. So I notice that there is no s square here. It means coefficient of s square is a 0. So I'll enter 0. Coefficient of s is 6. Constant term is 100. So that is the transfer function for I. So if I hit my enter button, it's going to give me exactly the same thing as here. So that is the first method of defining transfer functions. So let us move to the second method. So you notice that variables were stored in the workspace, so we can clear our workspace to do further defining of transfer functions. Then let us equally clear our command window. So let us move to the second method of defining transfer functions. Let us go back to that our first example. So this method is known as the S equals TF of S method. So we are first of all going to define S. We are going to say S equals TF of S. So if we hit our enter button, we are going to see that S has been defined as a continuous time transfer function. So with this S, we can now write back this function h of S and define it as a transfer function. So I'm going to simply write h of S the way it is. So h of S is simply 100 divided by s raised to the power 2 plus 6 times s plus 100. So that is my h. So if I hit my enter button, I'm seeing that h of s is exactly the same way as it is here. So h of s has been defined as a transfer function, as a continuous time transfer function. Okay, for your second assignment, you're going to define this I of s as a transfer function with MATLAB using the S equals TF of S method. So I hope you did it. I hope you were not just sitting down looking. So S has already been defined upwards. So in this case, I just define I. I just write in I. So I is S square minus 6 times S. That was for the numerator. For the denominator, we have S cube plus 6 times S plus 100. So if I hit the enter button, we are going to have I as this. So I is S square minus 6S divided by S cube plus 6S plus 100, which is exactly the same as this one. For the third method of defining transfer functions, clear the workspace, clear the command window. So for the third method of defining transfer functions, here we have an example. For instance, let us say we want to define the transfer function j of s equals this. If we want to define it using the TF method or the s equals TF of s method, we will have to break down this function into this form so as to have the different coefficients of s and the constant terms to be able to use them. But with the ZPK method, it is not necessary to break it down in this form. With the ZPK method, I can define the function directly as it is like this, with its zeros at the numerator and its poles at the denominator. So let us define the transfer function j of s with the ZPK method. So in this case, I'm going to say j equals ZPK. So for the first square bracket, I have the zeros. So up here, I can see that the only zero here is -1. So to find the zero, I equate the numerator to be 0. So if I say s plus 1 equals 0, it means s is equals -1. It means I have a 0 of -1 at the numerator. So for the first square bracket, I have a 0 of -1. For the second square bracket, I'll have to find all the zeros here, but zeros in the denominator are usually known as poles. So I have to find all the poles here. So while looking at this, I have a pole here of -2, I have a pole here of -3, and I have a pole here of -4. So I'm going to enter in all my poles. So I have a pole of -2, I have a pole of -3, and I have a pole of -4. Then after that, I have to give the gain of j of s. So usually the gain is a constant which is being multiplied by the numerator. So in this case, I can't see any constant multiplied by this s plus 1. It means the gain in this case is 1. So I'm going to enter in a 1. Please, if you don't understand this for the gain, we are going to solve in another example and you understand it better. So if I hit my enter button, it's going to give j as this. As you look, you see that is exactly the same as this continuous time zero pole and gain model. Let me give you another example, or let me say another assignment. So I would like you to define the transfer function k of s, which is this, with the zpk model. So I'll give you some time to do that. So I hope you have done it and you're waiting for the correction. So I have k equals zpk. So you remember, for the first square bracket in this case, we have the zeros. So at the level of the numerator, I can see if I equate the numerator to 0, s minus 1 equals 0. It means s is equals 1. It means I have a 0 of 1 at the numerator. So I'm going to enter in 1. So for the second square bracket, I need the zeros for the denominator, but I said at the level of denominator, the zeros are known as the poles. So I have to equate each of these terms at the level of the denominator to be 0. So if I equate this, and this to be 0, I'll have here s equals -2, s equals 3, and s equals -4. So I have as poles -2, 3, and -4. Then for the gain, I said the gain is usually multiplied by the numerator. So for the first example, we had this. There was nothing that was multiplied by the numerator, so we took the gain as 1. But for this example, we notice that there is a certain -5 here multiplied by the whole function, which is being the same as it's being multiplied by the numerator. Means our gain here is -5. So I'll enter -5 for the gain. So if I hit my enter button, so we notice that k is exactly the same as here. So that is a third method of defining